Hi, this is Abraham Kong, and today I'm going to talk about what should I know about cross-validation as a data science beginner. So the first question is, why should we know about cross-validation? So when it comes to data science, the machine learning model is a pen for data scientists to write a poem. And by choosing the right model, we have the ability to write a better poem. But since there are so many machine learning algorithms out there that let us to choose from, how do we know which one is better? Do we choose linear regression? Maybe Kierkegaard's model? Maybe support vector machines? Each model has its own bias and its own benefits. We really have to look deep into the data set to decide which one is more suitable. So here's the point where we want to introduce cross-validation techniques. It is a technique data scientists use to evaluate the accuracy of a machine learning model. Now, before I proceed to cross-validation, let me give a brief introduction to machine learning model. When we are building any machine learning model, we feed some initial data, also called training data, to train the model and throw another set of unknown data, also called testing data, to see how well the model performs over the future data. If the model performs well on the testing data, its results are consistent, and it is able to predict a good accuracy of future data inputs. We can consider the method to be stable. Now, suppose a data scientist has built a machine learning model and has the model trained and tested on the same given set of data. Now, even the data scientist is getting a 98% accuracy of the model outcome. It still does not mean the model is well trained and with high accuracy. That is because the model has seen the testing data already, and the results does not mean when the model faces the brand new set of data input, it will keep the same high accuracy. So here comes the main idea of the cross-validation. It is to have the data split into two portions, training data and testing data. We use the training data to train the machine learning model and perform tests on the testing data part. If the model performs well and has a good accuracy of the testing outcome, then the model is considered trustworthy. Now, come back to the original question of choosing between different models. Cross-validation is able to provide an accuracy score for each different model. And by using it, the data scientist will know which method to choose. Now, let's focus on how to perform the technique of cross-validation. So here is a diagram of the idea of split test and train for cross-validation. Within the whole data set, some part is considered as training data set used to train the model, and some considered as testing data set used to evaluate the model outcome. Now, the first method we're going to talk about is the holdout method. Holdout method is a widely used method in machine learning projects, and it is the simplest way to do split, train, and test. The data scientist will divide the data into two portions, just like the diagram we see before. The data scientist let the larger amount of the data set be the training data set, and the smaller amount of data sets be the testing of data sets. Depending on each cases, but the data can be split into 80% to 20%, 75% to 25%, 70% to 30%, or even 50-50 in some cases. This is considered an exhaustive type of cross-validation, and the split will happen randomly, meaning we don't know which data will be used to train and which data will be used to test. That comes to the downside of the methods. The testing result is in high variance. The evaluation of the model depends heavily on which data ends up in training set and which in testing sets. Thus, the evaluation might be different with different splits. On the other hand, the holdout method has a better runtime in computational cost compared to other cross-validation techniques. Let us use a simple data set in Python as an illustration. Now we have a simple data set with 1, 2, 3 to 10. And let us import the library from sklearn.model_selection. We will use the library of train, test, and split. Now, here's in the outcome, we can see 80% of the training of the data is used as training data. And that is because in the function, we call the testing data sets as 0.2, which is 20% of the data. Now, we're going to talk about k-fold cross-validation. In this technique, we divide the whole data set into k portions or blocks. While k can be any number, but k equals to 5 and k equals to 10 are most commonly used. Suppose we have a data set and divide it into 5 portions. We will use the first 4 blocks of data as a training data, and the last block as a testing data. Also, since we are dividing the data into 5 blocks, this is also called as 5-fold cross-validation. To avoid the high variance, we have in holdout method, the technique will iterate again to use the second blocks of data as testing data and the rest as training data. And we can see in the diagram over here, in the first iteration, testing data will be the first block, second iteration, the second block, and so on and so forth. So the iteration will be done until all blocks of data has been evaluated. After iterating through all the data sets, the technique will compare all the accuracy score and choose the highest one as a result. Now, each data point will fall into both training data set and the testing data set once. So here is the disadvantage of the technique. It is since it has to run from scratch k times, the computation cost will be way more expensive than the holdout methods. And of course, comparing to the high variance we have in holdout methods, the results for k-fold cross-validation is less unbiased. So let's look at what it looks like in the simple implementation in Python. So here we'll be using the same data sets as before from 1 to 10. And here in the function, you can see we use n splits equals to 5, meaning we have 5 splits, k equals to 5. And in the below output, looking at the testing data set, we can see the whole data set is equally divided into 5 blocks, and each block has been falling into data set of training data and testing data. Now, let us come to the last one, the leave one out cross-validation. This is a very similar to k-fold cross-validation. Leave one out cross-validation is the k-fold in extreme. Leave one out cross-validation takes each data point in the whole data set as a portion. Same as k-fold cross-validation, after choosing the first set of the data to be evaluated, We then iterate through the whole data sets to get a holistic view. In contrast to the holdout method, this method has a very low bias on the training results since every single data set has been trained and tested. And also contrast to holdout method, the computational cost for this method is extremely high due to the fact that the method will be iterate n times for a data set containing n numbers of data. Here will be a diagram, a GIF, to represent how live one out cross-validation will work. We can see that each data set, each data point is representing test data in different models, meaning different iterations. Now let's take a look at what it looks like with the same set of data from previous example. So this time, we will be importing from the live one out library in the sklearn model selection. And here, we can see from our test data set output, we can see from position 0 to position 9, every single data set has been tested and trained. Now, come to a conclusion. Cross-validation is a very useful tool when it comes to evaluating the machine learning method. Depending on the data set and use case, the data scientist can choose from using a method that is easy on computation or low on bias for the result. That will be the end of the presentation, and thank you for your participation.